Hi, welcome back. We'll talk about software security again, code reuse attacks, but a little bit of fun stuff at the beginning. I just read this news. A small village in Wales, United Kingdom, had this broadband problem every day at 7 a.m. for 18 months. And then their company, the ISP company, couldn't figure it out. Turns out it's an old TV set where some villager turned it on every 7 o'clock in the morning, and turns out the interference, electromagnetic signal interfere with the internet service. It happened to me once. I was in a talk. The speaker had its display problem, as it just keep shaking on the projector, and then they couldn't figure it out, and they were like, okay, let's just go ahead. And during the presentation, the speaker was playing a video and say, someone turn off the lights. And then all of a sudden, the problem went away. So the display interfered with the lights in that auditorium. But today we want to continue talking about software security. Just a little bit of quick recap. Last time we extend our vulnerability discussion, attack discussion to integer overflow, use after free, heap-based overflow, data-oriented attacks, and essentially different ways the attacker use to hijack the control flow and data flow. The typical way to hijack it when there's a control transfer, jump, call, return. And we also talked about the protection, non-executable stack, randomization at different granularity, canary word, and so on. We said again and again and again, please validate input. And you will see, even for code reuse attack, return-oriented programming, those fancy ones, just-in-time return-oriented programming, attackers still need a vulnerability as an entry point. Well-formed inputs is very important. You have to make sure that your program, you as a developer, ensure that all input coming from untrusted sources are validated. And we also, last time we also talked about, sometimes if you just have one bad elements, one bad apple is probably not very useful for attack, but then if you have external input without boundary checking, and then this input can reach sensitive elements, can overwrite pointers, address, and then data variables. Last time we talked about this flag, the authentication flag, those important flags. And then the sensitive elements is used to make decisions, impact the control flow, data flow. This is where things will get bad. And so if you can stop one, that will be the number one. That's the easiest for attacker to control and then prevent those attacks from happening. This is last time we saw this heap overflow example, but then just a different type of function pointer can be overwritten, list can be overwritten, and then it can be referenced, and that could be leveraged by attackers. An example where you see this the callback pointer, the function pointer, right? So it's supposed to point to a legitimate function, point to the address of a legitimate function where that function is stored, but could be overwritten, and then point to the attack code, or point to attacker's function, right? So it doesn't have to be stack. Things may go wrong. How to prevent those type of control flow vulnerabilities, unintended function execution. A very, very powerful and very popular, very well recognized defense is called control flow integrity, CFI. Last time we said that it's an approach that ensures the runtime execution follows the previously determined control flow graph. And you can determine it through static analysis, meaning that you don't run the code, but then you look at the binary. Or you can run the code in a clean environment and then get the more fine-grained, the graph, the expected behaviors. Sometimes the runtime information is useful, like, a branch, which branch this execution may take. And you don't know at a static time. You have to run it. So in general, you just have a better idea of what this program would do. And that would can be used as a policy to enforce the runtime behaviors. And so you sort of set a boundary of the program. Not this Thursday, next Thursday, our TA will present more information. And so stay tuned for that. So I want to talk a little bit more about code reuse attack and also antivirus signature today, and then start our discussion on OS security. Code reuse, last time we said that attack does not require new injected code, but it's a rearrangement of existing instructions in the victim computer, in the victim program, in the process memory, in a ways that benefit the attacker. And the specific type of code reuse attack that we will talk about is Return-to-libc attack, but there are also return-oriented programming. It's called ROP, R-O-P, which is a more generalized attack of Return-to-libc. There's also just-in-time return-oriented programming, and so it's different flavors. But you will see that it's essentially code reuse. There's no injected shellcode. And of course, these attacks came around the late of 1990s because stack at that time start to get more and more restricted. You cannot execute code on stack. Attacker needs a different way. And so why not reuse existing library code? And libc is standard C library. It has many functions, methods that enable you to intercept, transfer to kernel mode and then execute system calls. And so the first approach, this demonstration was done by someone in 1997. So that was 23 years ago, a long time ago, relatively long time ago. And why libc? Why Return-to-libc library? And libc is a very big, and it has everything. And researchers find out if you can access to libc, you can basically achieve whatever function attack function that you need. And so people call it Turing complete or arbitrary function. And so essentially it would consider the infinite amount of instructions, enough for you to complete basic attacks. And also very high privileged functions as well. And so what does, but very important to know, attacker with Return-to-libc still need an entry point. A buffer that is too small, there's no boundary checking or use after free vulnerability in the victim code. The only difference is that instead of having shellcode injected into the buffer on the stack, the attacker doesn't have to do it anymore. There's no new shellcode putting into the victim's memory. So let's see how it can be done. Let's just orient ourselves a little bit. So this is the stack that we've been using, this layout from left to right. Okay, some people do it this way or this way, but But so you have this small buffer, save the frame pointer and the return address, and then there's some arguments for this subroutine. And so there's just additional memory elements. So before, when we talk about Stack Overflow, we focus on this return address, right? Focus on this return address, and we said that we want to make sure this return address we overwrite the buffer so that the return address gets a new return address, and then it points to the beginning of the buffer or somewhere in the middle of the buffer so that you can execute shellcode, right? So we used to inject the shellcode here. But now you don't have to. You don't have to, because you only need to point, if you manage to find out the address of, say, a function, like say a system function in the C library. If you manage to find out the address of that, you can just write that address as a new return address. And then the victim computer will naturally return to that C library function, and then meaning that we'll be able to go to that location and then execute the instruction from there. No need to inject new code. And so the concept is very simple, and in reality there's some complication. For example, in this case, we want to execute, we want to just open the shell, and this is a command, a system, a libc function that allow you to do it. And so how can we pass in the argument, right? So all the function calls need an argument. And so essentially the attacker will do whatever it takes for you to complete this function call. And part of it is to prepare the arguments. And to prepare the arguments, you have to give the address of this string /bin/sh. And put it on the stack. So when this function call is executed, the argument will naturally pop and be used as an argument to this function call. And so this is essentially what attacker needed to make one call. And in this case, you don't really care too much about what goes into the buffer, and so you can fill out the arbitrary junk. Doesn't really matter anymore, as long as you point to the correct function in the libc library. So essentially you have to first find out the system function, the address of it, okay? And then by this, you should naturally think of the assumption. What is assumption? There's no ASLR. There's no, at least no fine-grained ASLR, right? So if victim's machine use the address randomization, and how can you find out the address? And typically we assume that if you can find out the address, that means in the typical setting, okay, means that you are assuming you do this using a debugger or whatever attacker on attacker's machine, and then maybe it's a complete replicate of the victim's machine. The victim has no randomization, that therefore the address is the same. The address space layout is the same, and then you can use that directly. So that's the assumption. And you overwrite the old return address, and then in the meantime you also find this, the string, the argument. This is the argument to that function address, and put it back in, and then you're done. So that's very high level what's happening. Biggest assumption is that there's no fine-grained address space layout randomization. Yeah, that answers this question. There's some more complications, and then there's a modern attack that really can actually bypass the ASLR. Hopefully we'll have time to talk about that next Thursday, in Salman's lecture. So yeah, sometimes there's an information leak vulnerabilities, like heart bleed type of, it's memory overread and there's the information gets leaked. You can use that to reverse engineering address randomization. But for now, let's just assume there's no address randomization. And the return to libc was designed to bypass non-executable stack. So in that regard, it is already very successful. In reality, there's a little bit slight more complication if you would like to exit after you open the shell. The attacker would otherwise you may run into segmentation fault if the execution is done and then the program returns, and then would not be able to find a meaningful instruction to execute. You may get error. And so you want to exit, you want to be able to exit somewhere after the shell is open. And so you put the exit function here somewhere and to make sure that it's the next instruction gets executed. But then, this is a function taking no argument in instructions, in binary instruction. That means you have to give it a null as an argument. And last time we said if you see a null in a string, the string will terminate. That means the end of the string, and then put it somewhere. You just cannot put null in the buffer. And so there are some tricks to make this happen. We'll not go into the details, but you just know that there are ways to get around this. And so that's the basic concept of return to libc. And of course, you don't have to execute the system function. You can execute whatever function that you need. But this one, open the shell, is very general. Once you open the shell, the attacker can do a lot of things. And so there's some technicalities when you actually execute this, and you're doing, a lot of you are starting to have questions about programming assignment, even for stack buffer overflow, executing, conceptually it all makes sense, but executing it, doing it, for real, is actually not that straightforward. And so, it takes a lot of trial and error. And by the way, the return to libc can also chain, so it's called function chaining. There are ways for you to create fake stack frame for one function, and once it's done, it gets executed. Another function gets executed. Again, you point to the function, feed it the required arguments, and then once gets returned, you point to an address of another function with properly arranged arguments, and so it's called function chaining. In that case, arbitrary functions can be done. There's many choices in libc. So it's very important to know, in terms of defense, the keyword is CFI. And the CFI is more effective than ASLR, because ASLR, address space layout randomization, has many flavors, many varieties. CFI, on the other hand, also has many flavors, but then very carefully done. It's a more direct way for you to ensure that the execution, the order of execution is expected. And so, of course, there's always overhead to security solutions. You have to understand the program. You have to know when something transfer, what is expected. And sometimes your estimation may be off, may not be accurate, or you don't have the information. For example, the function transfer depends on the user's input, and then you don't know ahead of time what the input may be, and so you may overestimate or underestimate, and that may cause some problems. So, for example, let's say if you overestimate, meaning that if you say, okay, I don't know which path it's gonna take. Let's just say both paths are fine. And then, but then in reality, only one pass is fine. Then you may permit malicious execution, right? But then if you underestimate, if you say, okay, I'm not exactly sure whether this pass is good or not, and let's just don't deem it necessary. Let's just label it as malicious, not allowed. And then in reality, it could be benign. And then you get a false positive, a false alarm. So return-oriented programming, and this was after Return-to-libc. This was, but more general, you don't have to jump to the beginning of a function. A function may have many instructions. You can actually utilize some consecutive function in consecutive instructions, and then be able to use those code snippets. But then as long as it ends with a return, you'll be able to sort of stitch with other gadgets. And so this gadget, this is a concept introduced by return-oriented programming. So people say rope gadget or ROP gadget. It's just some sequence, a sequence of instructions. It could be like 2, 3, 4, 5. And so here gives some example. If you see this delimiter, that's one instruction, and so on. And it has to end it with a return so that attacker will be able to transfer to the next gadget. And then be able to chain them. So there's this gadget chaining concept. And a gadget has a function, has a purpose. And in this case, this is a move gadget. So it's just to move one value into another value, into a register. And so everything else is not very important. So that those are non-core instruction. Only this line for this gadget, this line is the most important, and a return. And so there's, for like libc or with a reasonable size application, there's just numerous amount of this kind of gadget. And so essentially attacker can do a lot of functions. And once you have addition, move, and so decision, and so there's a comparison, there's a lot of operations a gadget can support. And so this is a very high level illustration of return-oriented programming, where you have all these, the blue lines represent the normal control flow, and then the attackers will be able to jump from one return to another return, from using return from jump from place to another place, gadget to another gadget, and so and be able to execute the existing code in the new order. So return-oriented programming is very, currently considered the most advanced attack, and then there's different flavors. There's also JIT ROP, just in time, return-oriented programming, which essentially would follow will be able to discover the gadget at runtime. The traditional way is, you just you can't like offline discover the gadgets where all the code snippets are, and chain them together statically. But then with ASLR, fine-grained ASLR, you won't be able to do it. So attackers discover it at runtime. And so instruction, last time we talked a little bit. Today I want to say a little bit more about instruction level randomization. This is where we find that it's actually very, very effective against code reuse. It's just like the gadget we showed before. If the return and the move change place, then that gadget is useless, right? So if the order is completely messed up, is destroyed. And so that's what we find out. We compared some existing randomization solutions. Some are, all of them are ASLR solutions, but then some randomized at instruction level, some randomized at function level, that is the most coarse-grained. Some at block level. Block is where, if you look at the control flow graph, whenever there is a control flow, the consecutive instructions between two control flow transfers is considered a block. And so if you have, say, if statement, and then within the if everything gets executed, then that's one block, the if branch. And so here is a percentage, right? This is 80%. What is this? This is the reduction in various gadgets. So we compare with and without ASLR. How many gadgets are there? And then you can compare how many gadgets disappeared with ASLR applied. And you can see that with the instruction level randomization, this two type of gadgets gets a huge reduction, right? 80% reduction, that means only 20% of them are intact. And on the other hand, if you do function level randomization, that means this function is placed, the offset at the beginning of this function is placed randomly, but then within the function, instructions are still sequential, and you still be able to find the gadgets. And so majority of the gadgets were kept here, right? Not very useful. And so that's very interesting. This is very interesting. Also very expected funding. And by the way, this is for applications we tested. This is for library we tested. Without libc though, this libc, none of these tools can randomize libc because it's just so big. And also we find that it's very interesting for some of those randomization tools to work, they have to use C library, and so you cannot randomize it and then use it. Like you cannot run yourself so that it actually randomizes libc, and then it just become a chicken egg problem. And so that I think, so essentially no one can randomize libc. After like 23 years, people find out you can use libc to do code reuse attacks. We still don't know how to randomize libc. But disrupting instruction order, and so last time we showed that normal programs still can work at the instruction level ASLR because there is a secret mapping that will tell you where to find everybody. Okay, but then without this secret mapping, everything will look so far apart. They are not consecutive, and so you cannot just to read through the code page, and then find everything before you can, right? So it's very convenient. You see, this is a return, and so this will be useful. This is a lot of them will be very useful gadgets. And so that's our discussion on code reuse attack. And of course, next Thursday we'll have more discussion on this topic. And but I want to switch topic and talk about antivirus scans. And it's very important to know this is the first line of defense. Some people think, oh, AV scan is so basic. It's not very useful because it cannot be effective against the zero-day malware, the new malware, because you don't have the virus signature, but at least to protect your system against existing malware, right? So do install AV scanning scanners, Symantec, I believe we all, it used to be the students can get that for free. I'm not sure anymore. But there's free versions of AV scan. So I encourage all of you to consider using it. And if you work in a company and your boss say, please tell me what's the first line of defense, what should we do? Tell them that you should all install AV scanner. So what is a virus signature? A virus signature is just some string, some characteristic string that appears only in malware and infected files, but not in legitimate uninfected files. And so here is an example, right? There's this URL is part of the virus scan. This is from Kaspersky Lab. And so it's very important. Otherwise, if the signature are not very carefully evaluated, also appearing in legitimate files, then you will have false alarms, which is undesirable. And the basic function of AV scanner is pattern matching, right? Pattern matching, string matching is the basic function. And I want to show you, some animation that is illustrate how string matching works, and then there's just different ways of doing it, and those are very classic string matching algorithm, is still very fast. And so let's just see the Boyer-Moore algorithm. This was invented back in the 70s. Very, very fast, very effective. And so suppose this is your file, okay, like your Word file, whatever, and then you can change, you can it's a binary or whatever encoding that you can you can use to represent, and this is the virus signature, okay. And so Boyer-Moore goes, it's very fast because it always starts with the last character. Now you see it's mismatch, right? Mismatch, there's no need to compare anything ahead. You can just shift the whole thing, right? And then what happened is that they put some fictional s here, suppose that this is s, but it doesn't really matter. You compare the end of the pattern, right? E versus P, also it's a mismatch, but then this time is different. You cannot shift all the way to the end because there is a P here, so there is a chance that it's a match, and so you will align P, and then you go from the end to the beginning. So you see, oh, E and E, good match. L and L, good match. P, M, good match. Whoops, here you see a mismatch. And then you shift all the way down. And so the way that you do is that you go similarly, you go from the end and then you shift, you align the position where there's a match, and then you go from the end. In this case, it's exact match. And it's a slower, but then still pretty good algorithm. Is called Knus, Brett, and Morris. It starts from the beginning, but then you see this is a slower, and then if it's a mismatch, you go one by one, and here it's a match, and so it doesn't work. You go down here, and so you see it's move a lot a lot slower, okay, and so it goes to the end. So to go back to our slides. And so this is just to give you some intuition of how the basic operation of scanning. Nowadays there's this tool called, there's a website called Virus Total. Virus Total now was several years ago was purchased by Google. It's online aggregator of virus scanners. It's I think it's a collection. Right now it has 7 antivirus scanners, and so it makes sense. Why just use one? Maybe we should use a whole bunch of scanners, and that would just make it more comprehensive. And then if one is not very accurate, hopefully others are. And then you can decide, based on the votes, whether a piece of program is malicious. It also aggregates a blacklist service. It's free. You can upload files. You can ask it to scan the file, scan the URL, and so it's quite effective. And also it can scan like Android, a lot of Android APKs. You can say, oh, is this Android? Is this app a good app? And upload it. It will be able to tell you what do all these scanners think. And of course, the evasion of scanners. So we started talking about this at the very beginning of the class. We said that if attackers know how you detect, then there may be ways for the attacker to bypass the detection. And so I find several interesting examples of illustrating how this could happen. And so WCE.exe is a malicious executable in Windows. It triggered 47 scanners in Virus Total. However, if you just randomly change the welcome message in the program, just change the upper lower case, okay? Like this person has done, 5 of the scanners will think this is fine. And so even though 47 of them still are not fooled by this small change, the upper lower case. And obviously when you write signatures, make sure that you consider, make it case insensitive. And another example of invading AV detection is encryption. So without encryption, 47 scanner think this is bad. But then if you use a known program, Hyperen, to encrypt the executable, only 28 scanners now complains. All the others would just stop complaining. And so clearly those previous scanners, the majority, like almost half of them, have signatures only based on the unencrypted version of the malware. And so let's talk about encryption then. Encryption is, there's different way of encryption. You can use a key, but simplest way is to do, say, XOR, okay? So you have a key, like random, you randomly generate something, and then you do when you encrypt, then you XOR it. When you decrypt, you XOR it again, and then it's canceled out. And of course, when you decrypt, it's part of the key has to be part of the encrypted program so that you know how to decrypt. And so for example, you can have like junk looking code, but then there are certain parts that you cannot encrypt, right? So those the beginning, those preamble has to be in clear text, plain text, and so that it can be executed. You have to bootstrap the face, and then you decode it and then you execute the decoded version, right? So this is obviously very intuitive. Polymorphic virus is called, it's where that the key gets changed. And so every time you encrypt something, the encrypted version changes, even though the code is the same code, but then the encrypted version look very different. And so and there's a lot of randomization functions. Can generate a new key, and then you do XOR, then it's the resulting encrypted code will be different. Metamorphic virus is one notch up above a polymorphic virus, where the instruction orders, the decrypted order actually changed. And then there's many ways for you to achieve the same function, but then with different looking code. You insert no op, some random jumps, and some arithmetic that doesn't do anything, right? So you do like, some counting and so on. The instructions will look different, but then it's even after decrypted, they look different. So with all those different sort of changing form of more like polymorphic viruses, how do you detect, how would you be able to tell that this is something that are bad? And for polymorphic virus, and recall this is where the key, it changes every time the virus encrypts itself, but then the code is still the same. What you can do is that it just decrypt it, right? So you have a virtual machine, a test environment, you just decrypt it. The code has to be decrypted in order to be executed. You just run the program and see the memory region, which is actually decoded, and allow you to apply signature scanning and so on. So this is very intuitive. We'll have a couple more slides for you to take a look. But essentially, once this is decrypted, you can look at the memory region, look for telltale signs. Metamorphic virus is harder, but there could be strings that they has to achieve, and so, but anyway, as we talked about, it's very hard for you to know for sure that you can detect something, because it can easily be bypassed, and an attacker will try different ways to bypass a detection. So that's AV scanning. So here is a little bit, as we're talking about software, how different software can go wrong. I also show you, let me show you a video. Okay, let me start sharing. Okay. Oh, this is very blurry. So this is a code red worm in 2001. And this is the second version. There are two waves of code red worm. Two versions of code red worm. And this is the second wave in the summer. And I hope that you notice, you can go back and then take a look again. There is a huge jump at a later time where it's just very quickly everyone is infected, and by that time it was one of the biggest internet worm outbreak. And so, and I remember it was attacking a Windows IIS. It's a Windows version of Apache web server. And so epidemic curve, epidemics, Ebola, COVID, worm in this type of infection, what it does is that it has a slow start, and you're like, okay, this is not that bad, and then once it's because it starts to grow exponentially, one infected computer will infect a whole bunch of other computer because its job is to propagate. It's keep connecting to other computers that are not yet infected. And this is I got online. It's 2014, the African Ebola outbreak, and so you see it start picking up very quickly. So early prevention is extremely important. Early prevention. And similar with COVID, if you detect one case, you have to really test like 7,000 cases to make sure that everybody are infected gets quarantined. Class project idea, something about VirusTotal, maybe analyze the result, run some known data set, think about it. And I mentioned before, this goes back to the things that we talk about here, AV scanning. The virus can change its behaviors, and so it's really impossible to detect completely. So no one, don't say, hey, I have a product that can detect completely all viruses. Don't even say that. You can try to complete be as complete as possible, as fast as possible, but you just have to know your limit. And so I want to switch gear to talk a little bit more about operating system security. Operating system, and I'm thinking maybe we should start to talk about CPS first because it's more interesting. Industry control systems like this. Before, people don't think too much about, why should we worry about cybersecurity, but now, but you look at this, it's a lot more complicated than typical, say, IT company, because besides information technology assets, you also have operation technology assets, OT, right? And so all of them can get infected. In ICS, there's also other names, SCADA, supervisory control and data acceleration. A lot of them basically essentially talks about you have IT component and the physical component, right? So for example, you have heater that has a control, has circuit boards, but then there's also heating. It actually heat up the physical space, right? So there's a physical environment, and then the control action, heating, cooling, will influence the physical environment, but then the computer make decisions. But the computer make decision based on the physical environment, based on the temperature. So there's this infinite loop that's going on, okay? And this is the biggest characteristic of cyber physical systems. And there's a feedback control loop. And so it's very different from regular, like Apple machine, laptop. There's no, the computer will work regardless of the room temperature, right? So it's very different. Now you have to know, does the control program working well with respect to the physical environment? You just cannot tell by the program itself. And sometimes it should heat up, sometimes it should give the cooling command. and those decisions based on the environment. And so the actuator is the device that actually open the valve, start the cooling, start heating, and so on. And so you just, whenever you see ICS, CPS, there's this feedback, there's this loop kind of thing, okay? So it's very important. There's a controller, there's device actuator, there's collect sensors, and then they are connected to the feedback loop. So feedback loop sometimes may be compromised, and in this is 6 years ago now, a German steel mill was breached, and the mill couldn't shut off, and then caused massive damage. And it all started with spear phishing. Okay, and this is where the IT breach leads to the OT breach, right? The in information technology asset vulnerability leads to the operation technology asset. And so some hacker gets hacked into Office network and control management software, take over the plant's control system, and compromise the human-machine interaction. This is where the operators will be able to monitor is a steel mill working properly, and then in the end the furnace cannot shut down. Really bad, very scary. Not PT ransom. This was very well known. It's a ransomware. This is a screenshot. It asks for 300 worth of Bitcoins. 300 dollar worth of Bitcoins. So and then be able to get, if you pay, then you'll be able to get the decryption key. There's a very short video from CBS talking about the now PT cyber attack, and turns out a lot of the one of the defense, one of the solution was a computer that was taken offline due to maintenance, and that end up saving the day because it is not attacked, and so people use that computer to restore the other infected computers, and so that was and it was considered, this is I think widely known as a Russian attack, and because PTA was means little in Russian. So this is and we mentioned this before. Backup really works as a deterrent, as a mitigation of a ransomware attack. CPS security is now known, not new. Last time we talked about Sirax 25 incidents, and so what happened is that you have in the normal this radiation motion in the normal mode, it's a low current beam, then this metal plate is away. But then if it's a high current X-ray, the metal plate is in place, and then be able to act as a screening and a filter and measure the dose of the radiation, blah blah. And then the problem at the time of the incident is that the plate was away, is not in place, and then therefore the operator keep increasing the dose because the screen seems to indicate there's no radiation, and end up one of the patient described a very hot beam of radiation, strong beam of radiation, shine down on the patient's body, and so you can like literally felt it's very hot. And of course, you know, I think one of the patient had to do had to have hip replacement surgery, and then passed away after infection due to the hip replacement surgery. And so it was really very devastating. So CPS security, CPS is equally important as regular OS security when you talk about Windows, Linux OS security. And then people are less well studied, and also less it's hard, you know. A lot of researchers don't have the resource and access to the CPS systems, and, you know, oil power utility companies. You really have to establish collaborations with those folks for years and years in order to get access to some internal operation and understand what do they need. And so it's hard to help them. Time sensitiveness of CPS, and this is also very new. Like your computer, if it's hacked, I mean, it will not immediately crash and burn. For, you know, big providers like Google, Amazon, they will have some fault tolerance, redundancy. But then if you're talking about airplanes and flying or in the mid-air and got hacked, it will fall down. And so this is you know, I'm not going to play it, but take a look at a drone in some hacking demonstration will immediately drop right away. And so that element is very challenging. It's new. That new requirement a conventional computing system does not face that kind of challenge. And so your security defense, your solution has to be quick, has to switch in right away, simple, and so easy to adopt in practice. And so a lot of interesting, and so I encourage some of you for your class project to also think about CPS security. And so, by the way, we're gonna have something due, the class project proposal due. I want to come up with the assignment today or tomorrow. So look out for that. I think that's it for today. We'll see you on Thursday. Thank you.